Okay, so today we are starting to talk about components. The first component I will be introducing is gear. Different from what you have learned in other courses, such as design of mechanism or dynamics, kinematics. This course introduced gear design in a different way. Okay? In this course, we care about whether the gear will break. Because this is a mechanical design course, we care about if something will break. We don't care too much about mechanism or dimensions of the gear. Okay, that's not the main focus. So if you are more interested in calculations for the gears, for example, I have 5 different gears connected to each other. I want to calculate the speed of some gears. Okay, that's not the main topic in this course. Because starting from now, we will be talking about chapters of mechanical components only in a week. So I won't be able to have proper notes. So I will just use the slide, and the pictures are taken from the textbook. Over here, you maybe need to know about the names of the gear. One important circle is the pitch circle. Okay, so the pitch circle represent like averagely where the force transmit from the other side of the gear to here. It's like an average position. Why do I say that? Because for gears, you always have pairs of gears. So let's say you have one gear here and another gear here. They should be contacting with each other. Okay? So you may have a contact point here, and on the upper side, you may have a gear teeth like this, and on the lower side, you have gear teeth like this. Okay? So during the contact, during the process of this contact, usually there's a point connection. Okay, and as this motion starts to affect the motion on the other side, when one side of the gear rotates, the other side of the gear, of course, rotates accordingly. This kind of tight connection is called a conjugate motion. Conjugate. This word is a key word. So in Chinese, it's called 共二, right? Because if you just learn from English word, you may not even know what does conjugate mean. So when two things are tightly related, connected to each other, and they have relative motions with each other, then we use the word conjugate. Okay? So they have this kind of conjugate motion. And the slope of the teeth is very important. So right here, you can draw a line. It's like a line of the pressure. Okay? So it's like from one side of the gear, there's a pressure applied from this side to the other side. Okay? So the profile of the teeth is so well designed so that when gears are having this conjugate motion, this pressure stays on the line. And let me make a drawing of some other moment when the teeth rotate. So let's say this is rotating clockwise, this one is rotating counterclockwise, and let's say this teeth moves to the other position like here. Then the upper half, the teeth will be moving like this. Okay? And they are keeping this contacting point, but somewhere else. So the contacting point doesn't stay on the pitch circle all the time. The contacting point between this gear and the other half will be sliding along the edge of the teeth. Because when two teeth start to interact, the contact point may be close to the tip. And when it starts to do this conjugate motion, the contact point slides down to the root. And then when they start to get away from each other, the contact point slides back to the tip. Okay, so we're not trying to learn how to make drawings of the teeth profile so you can reach this. We just want to learn about how the forces are interacting between two gears. And for regular gears, the force applied between two gears basically follow this line of the pressure. So if you have if you make a drawing like this. Oh, by the way, when two gears connect with each other, the bigger one, we usually call it the gear, and the small one we call it the pinion. So when you see the word gear and pinion, the word pinion means the gear with smaller diameter. Okay? So when you have, in the future, when you see descriptions about gear and pinion, that means, okay, this one is the gear, this one is the pinion. Okay? And sometimes you may even see rack and pinion. What is a rack? So rack is a gear with infinite radius, super large radius. So it becomes a linear gear. So it's like something like this. This is a rack. Okay, so if you have a smaller gear that is connected with the rack, this one has an infinite radius. This one definitely has a smaller radius. So when you have a rack and a smaller gear, of course the smaller one is called the pinion. That's why you see these terms, rack and pinion, because rack is actually a gear with super large radius. Okay, so when you draw gears and pinions like this, when you make a circle that is tangent to each other, basically you are drawing the pitch circles. Okay, and this is where the pitch circles has contact. And usually you'll see something like this and showing you an angle. So basically that is the line of pressure. So this is basically the pressure angle. So this is, if you see a drawing like this, this is basically indicating when the gear interacts with each other right at this tangent point, the pressure between both of them follows this line of pressure. Okay, and why is it important to this course? We need to know how the forces are being transmitted from one side to the other side, and when we are making mechanical design, we need to know how much load that is being applied to some components. So let's say this gear is installed, for example, in a shaft. Right? Let's say this is a shaft system. Maybe there is a bearing, right? Just like any problems that we solved in the past, there's another bearing. And right here, right in the middle of the shaft, you install a gear, and this gear is interacting with another pinion on the other side. Maybe here's another shaft. Right, so two shaft systems connected with each other by the conjugate interaction between the gear and the pinion. Now, when we have shaft design, what do we care about? The loads inside. We care about whether there is a stress concentration, if there is any part that could have fatigue issues, safety factors. But what do we need to know first? The loading, the loads. So you have to know how much force is going to be applied from one side to the other side. Okay, and let's say we have a motor right here. Here's a motor that is driving this gear. So you basically have some force being applied. So this pinion is driving the gear. So in this case, we have this a force coming from the motor, and we can assume the force doesn't, you don't lose any power. So 100% of the power is being applied to this contact point, and then pushing the gear. So by doing so, you can estimate how much force that is applied at the tip of the one of the tube, right? Then you know how much force is driving this shaft system. Okay, so in this course we care about the direction of the force, position of the force, and how it's related to the driving power. Okay, so if you have this pitch circle from this on the side, we call this. This is the this is called the face. Okay, on the side, this is called the face. But the upper half is the face. The lower half is called the flank. And if you compute the distance, the height of the face and the height of the flank, they are called the addendum and dedendum. Okay, so since we are in we may be reading textbook papers in English, so please learn those English words. So at the bottom, right here, there is a base circle, which is not mentioned here in the slides later. I think that's pretty much you need to know. Okay, if this circle is called a pitch circle, then how do we compute the pitch? So pitch is usually describing the distance between one pattern from the other pattern in some kind of periodic sequence. So along the entire pitch circle between two neighboring teeth, how do we compute the pitch? We basically compute the pitch along the arc, from one edge to the other, to the same edge on the other tooth. So this arc length is called a circular pitch. Okay, so it's the arc length, not the direct linear length. So after knowing those terms, there's some equations. Okay, so you probably have learned those in the past, but later on, when you try to compute some of the forces, you may need some of those relationships. capital, small p is the circular pitch, basically the pitch between two neighboring two teeth. So small p is right here. Small d, pitch diameter, which was mentioned earlier. Number of teeth, easy to understand. So what are capital P and small n? So let's just check on the definition. They are related based on the two equations on the top. So capital P is number of teeth over pitch diameter. So per pitch diameter, how many number of teeth you have, something like that. So it's like the number of teeth per length. And if you reverse this, if you have pitch diameter over number of teeth, then it's like a per teeth how much pitch diameter you have. It's like a ratio. So that is your module. Okay. And usually, manufacturer can only produce gears in certain number of modules. You cannot design your own module traditionally because they use machine tools and like some kind of cutter to cut, to form the shapes of the teeth. And the tool of the teeth cutter is designed in certain modules. Okay, so traditionally you have to follow certain numbers of modules like these. They give you certain numbers. Why do they define modules in those specific numbers? Because they only have tools for those. If one day you want to design a gear with a unique module, for example 9, maybe the manufacturer doesn't have the tool to make it. So what do you do in that case? You probably need to manufacture the cutting tool first, maybe by CNC machine or something else. So it's like a customized profile of the gear. So designers tend not to do that because it's more troublesome. But nowadays you may not be, nowadays probably you can 3D print or laser cut a gear. So customized dimensions could be possible. However, I'm not the expert in gear design. If you want to learn more about gear, you can take the course from Professor Shi Yipei in our department. She's the expert in gears. Okay, let me move on. This is basically the conjugate action that I'm talking about. And why are they drawing the shape in this unique dimension, in unique shape? This is just an illustration of conjugate action. So any two things that has this tightly connected motion and one movement affects the other side, you can call it the conjugate action. Okay? And the contact point rolls or slides along the edge. So another conjugate action can be seen in cam and follower. Cam and follower. Right, so cam is a shape that is not circle, but rotates about some kind of shaft, some kind of rotational center. And because of the weird shape outside, you have a follower. So sometimes it's a roller. So by having a cam and a follower, when you rotate the cam, this follower basically move up and down. So where do you see cam and follower? In engine. You know, in the engine, when you have the piston moving up and down, compressing the gasoline inside the chamber of the engine, and you have this moving up and down motion driven by the crankshaft. Okay, but piston is only having this motion for pressurizing the gas inside the chamber. It doesn't provide inlet and outlet of the gas. So you need to have valves opening, allowing gasoline coming into the chamber, close the valve, and then ignite to have explosion. After explosion, you will have the waste gas. You need to dump it to the outlet. So you always need to have timely controlled valve opening a small hole for the gasoline coming into the engine, close it for explosion, and then open another valve, release the waste. So the valve are moving up and down in certain time sequence. Usually those valves are controlled by cam and follower. And the cam and follower is following conjugate actions. Okay? Now, this is talking about the involute profile for the gear teeth. Again, I'm not trying to teach you how to make drawings of the teeth, so you just take a look. Okay, so this is an introduction of the base circle. When you have this bigger diameter, this is the pitch circle, which is contacting with the pitch circle on the other side. And then you define what will be the pressure, line of pressure. Once you have that, there will be a tangent circle that is tangent to the line of pressure. That tangent circle basically is called the base circle. So what does it mean physically? If you have a tooth profile coming from one position like here and start to move, this B point is the most possible point you can have contact with the tooth on the other side. Similarly, when this tooth start to have this conjugate action, and at some moment the teeth on both sides will get away from each other. So A point will be the last possible point where you may have contact. And the real contact point probably even will be inside A and B. It doesn't go outside of A and B. So the contact point could be shorter. Okay? And for engine gear designers, of course they want the contact length to be longer because it will make the gear pairs to be more stable. Because if you have longer time for the gear teeth to be contacting with each other conjugately, then you have good transmission of the pressure from one side to the other side. If you only have very short period of time of contact for each pair of the teeth, then you rely on pressure connect transmission between along one pair of the teeth, and then you rely on the other pair of teeth to take over the transmission of the pressure. So sometimes the pressure distribution will not be well transferred to the other pair of the teeth. So if you can have longer connection of the conjugate action, that's better. But again, that's the
concept for gear designers. Let me see what else you need to know. No.
Yeah, never mind. I think it's fine.
I don't want to talk too much. Now we need to know. Yeah, I already talked about the line of pressure, and this is basically the, like I said, base circle, the radius of the base circle. And because of the geometrical relationship, by symmetry, and this is a 90 degree right here. So pressure angle, this is also pressure angle here. So by the geometry right here, you can get a cosine relationship between the radius R right here, pitch radius, and also the RB, the base radius. And they are having this cosine relationship related to the pressure angle. Okay? What else you need to know? Now, let's talk about rack and pinion, like I said. Earlier, we mentioned about gear and pinion. Now we talk about rack and pinion. So for the rack, just treat it as a super large gear. So the linear pitch line is just like a super large circular pitch circle, right? Super large. So it becomes a straight line. And when you try to compute the circular pitch, basically measure the distance from one edge of the teeth to the other neighboring teeth. Then that's how you compute the circular pitch. Besides those, you can also observe the pitch along different directions. So for the rack, they sometimes try to observe the pitch not along this horizontal direction. They try to observe along this, you can say, pressure angle direction. So it's like along this pressure line, how long do I meet the other teeth? Okay, from one pitch to the other one. So it's like you're computing the pitch along this line of pressure, and it's called the base pitch right here. Okay, because the pressure line is related to the base circle. So if you do that, by geometry, you can have this cosine relationship again. Okay. There are some exercises in this chapter. I don't think I will cover those. Just basically applying those equations and trying to compute some of the pitches. But right here you see a new kind of gear and pinion. You notice that the teeth is not straight. They are not straight gears. The teeth are like tilted. So they are called the helical gear. So the teeth profile is following a helical curve, like a spring. Okay? So when you do that, you introduce a new angle, basically so-called a helical angle. You describe how the profile of the teeth change its angle rotated about the axial axis, the central axis. So there is an angular difference. Okay? Originally, this is your rotational axis. Originally, your teeth profile are
parallel to your rotational axis. But now they want to follow some kind of helical curve, so the teeth profile is now following some kind of helical curve. Okay? When you do that, you will have this helical angle. By default, a straight gear has 0 helical angle. Now, it's telling you the helical angle is 30, like the drawing on the left. Okay? So, geometrically, when you compute the pitch, you can compute the pitch in 3 different directions. I remember there's a. Let me find it. Let me find where. Oh, here. This is the helical gear. So it's like this is the rotational axis, and the tooth profile tilts. So it's following a helical curve. And if you try to observe the teeth, if you walk along this transverse direction, you will see this. If you walk along from this point to the other point, you see a teeth profile. But you are walking along this transverse direction. And this profile looks exactly like the straight gear. Now, if you change how you observe, change the way you take the walk, you now take the walk along this direction. This is basically after you rotate your observation by the helical angle. Now you walk from here to the right. You then will see this cross section of BB. You also see a gear profile. But this time, the geometry right here and the geometry right here won't be the same. Because earlier, when you walk along AA, the width would be wider, right? And if you now walk along BB, the width will be shorter. So, since when you take a walk along the tooth profile, along different direction, you see different periodic distance. So they try to compute they try to compute the pitch along different directions. Okay? So right here, if you compute the pitch along this transverse direction, they call it PT. So T represents transverse, like a horizontal. Okay? And if you compute along this one, then they call it PNs, because it's a normal to the helical, it's like a normal to the teeth profile. When you compute this distance, is normal to the teeth profile. So they call it normal pitch. And think about it, if you now try to walk along the axial direction, you actually will see another teeth profile again, but it's not very obvious. Let me show you. So let's say this is a helical gear, and here's the profile. Okay. So now, if I walk along this direction, and let's say this is one tooth, and this is the other tooth, right? So this distance is the normal pitch. Now, if I take a walk along the axial direction, then you will see from this point to
this point, I see one periodic pattern. So the pitch right here is called the X. So they call the pitch along the axial direction. Okay. And if you compute this one, this is the pitch transverse. Okay? So people try to compute those. Why is it important? Because for us, we want to know when there is a force applied from one side to the other side, where is the position for the force, and then what's the angle. And the direction of a force is very related to the geometry right here. So I would like to move forward to show you what is more important to this chapter, to our, I think it's in the other chapter. Chapter 14. So once you understand about this, the geometry, where is it? Oh no, it's actually in 13. We'll find it. Here. So this is exactly why we need to know about pitches along 3 different directions. Because later on, when we try to figure out the forces from one side to the other side, there will be 3 different force components between the pinion and the gear. Okay, and they are following those angles. And the angles are, of course, related to the profile of this helical curve. Okay? So, traditionally, when I teach this course, we will do some exercise. I think when I was in Zhongyuan, we even take exams in this chapter. It's a chapter not very easy, because sometimes students have difficulty understanding about the geometry. Let me show you why this chapter is, that geometrical sense is important. So this is a exact example that I mentioned. We have a motor that is driving a pinion, and this pinion is driving a gear, and there's a shift on the gear. So this problem may be asking, okay, what would be the reaction forces for the bearing? Okay, then you need to figure out how much force is being applied between the pinion and the gear. And because of this helical profile, there won't be individual force. And there won't be a force along this simple direction. There will be forces along all 3 directions. Okay, because when the teeth profile is helical, it's a 3-dimensional surface that is not parallel to x, y, and z. So the force that was applied from one side to the other side is following certain direction. So you have two teeth profiles, and let's say our classroom is our coordinate system x, y, and z. So the contact point between the two teeth for helical gears will be somewhere in the space, and the tangent force is normal to the surface, and that force vector basically is not parallel to x, y, and z. That's why we need to compute the force components along x, y, and z in this configuration. And when we do that, Wt will be generating torque because that's the transverse force that drives this gear. And Wr is like a single force pushing toward the center. So for the shift, what does the shift feel like? So let's say this is the shift, and here's the gear. So it's like there is a single force being applied from the other side of the gear. So what does it do to the shift? It bends the shift. So it's like it's a force that generates shearing force, and it will bend the shift. Of course, bend a little bit. And how about the force along the axial direction? So usually when we have a shaft system, let's say we have the bearings, okay, and let's say here's a gear. And if we realize there's a force following the axial direction, then we may have a machine right here, right? This could be a machine. So when you apply this force, that means you may have reaction forces here. Okay? So the other pair of the gear is pushing this gear, pushing this shaft, so there will be reaction forces along the axial direction. So it's a force balance problem. You may need to look into the geometry and think about, okay, does the reaction force along this axial direction affect anything? Okay, if the machine, the structure of the machine is very strong, then you probably don't need to worry about anything. You can just ignore the force balance right there. However, if one day you have a machine, for example, like this, and there's a hole, and you have a shaft system, for example, you have a shaft system like this, and you may have a motor at the bottom, okay, and then driving. And right here, you have your, let's say this is your bearing, and let's say here's the gear. And like I said, you may have forces coming down, right? Because the pinion, if you are using helical gears, and you may have forces driving down, and also the weight of everything. So the bearing there will be some forces that is holding the whole system, and you have reaction forces applied to the bearing. And if you take a deeper look, probably you will have design like this. So this is the shaft, right? If you are having some weight coming down, so the force will be applied from this small surface from here, applied to the bearing, and then you have reaction forces coming here. So for the bearing itself is being clamped, right? If you have a design like this vertically, you not only need to carry the weight of the shaft, you may also need to carry the vertical force coming from the other side of the helical gear. So it's actually an extra load coming down. Okay? So you may need to worry about, is my geometry right here strong enough? Maybe the bottom is a base plate. Okay? So it's like a plate. Is the plate thick enough will the stress concentration right here affect the geometry? So for mechanical design, it's all about stress, deformation, failure, fatigue. So force distribution are everywhere. Okay? Now, for today, we learn about what will be the force interacting between two gears. Okay? So that, I think we are reaching the end of today's lecture. I will continue on more of those in the next week. Let me remind you let me just preview what's gonna cover next time. So once we understand there will be forces between the gear and the pinion, we next will care about whether the tooth will break. So for the tooth, there will be forces, like I said, transversely, vertically, and of course, this is transverse. No, this is axial force. This is axial direction. This is transverse direction. This is like a radial direction. You have forces along 3 different directions. Which one may damage the teeth the most? Actually, is the transverse one, because the transverse force is like a force that tries to bend the tooth. So if the transverse force is too large, the tooth can break. So if you 3D print a gear, the most probable failure you can have in a 3D printed gear would be crack at the root, because the transverse force is bending the tooth. Right? So next time, once we know there are actually forces applied to the gear, next time we talk about the stress analysis inside the tooth. Okay, and there will be a bunch of models for this. So see you next week. Okay, so for today, I think you want to do the attendance check. If you haven't done that, please do so. If you finish